Hey everybody, this video is on wisdom of the crowds versus groupthink, learning in groups and in isolation by Mayo, Wilson, Zolman, and Danks. The paper is concerned with this central question: what methods of learning work well for an individual but not for a group, and vice versa. So let's first get a feel for the basic model. I'm not going to get too deep into the technical details here because I don't know that it's going to be too helpful for me to spend 15 minutes regurgitating math that they have themselves. Instead, I'm going to try to just give a more intuitive grasp of the model and the results that they find. So the model consists of a network of learners, and each learner in the network is going to choose some action to play each round. And the idea is the action is going to yield some payoff, is going to probabilistically yield some payoff. And ultimately speaking, as the number of rounds goes to infinity, we want to be able to find the actions that have the highest payoff. So this is determined by a person's method. So a person's method will take as input all of the actions that they've seen be taken and all the outcomes that resulted from those actions. And the method will tell them what probability to distribution to set over the actions that she can take. So based on what you've seen the actions do so far, the method will tell you which action to take now, or what probability to put on taking one action or another. So generally speaking, a method will take the actions that have had the highest payoff so far and try to put a higher probability on those. So generally speaking. So that's a bit of the general model, but let's get a feel for what context that we can think of these methods working in. So a method will work if it can find that optimal action in the limit. So now we want to know the different contexts in which it could do so. So the first and the simplest context is when you have just a single agent with nobody else in the network, and she's performing this method. Will she be able to find which action is actually optimal in the limit? In theorem one, actually, so this part isn't so much about results, but theorem one says there are in fact methods that do this, that allow you in isolation to find the optimal action. But our interest isn't so much it's just that there are particular algorithms that do any one of these things. Our interest is that there's going to be particular algorithms that do one but not the other. And so the idea is there's going to be certain algorithms or certain methods, certain ways of learning that work while we're in isolation, but don't work when you're in a group, or work when you're in a group, but not in isolation. But that's getting a little ahead of ourselves. So let's look a little bit further. Another context in which a method might work is when a single agent is surrounded by other people and you don't know what's going on with or you're not guaranteed to believe that any of these people are using the same method as you. So what happens to our learner when she's using a particular method, but she's surrounded by other people using different methods, and she's getting evidence from them too? So is her method going to be able to get her to the optimal action in this scenario? So another way we could change it, or we can think of a different context, is if we have some particular agent, but now she's surrounded by other agents that are actually using either the same method or a method from some family. So here we say that a particular method is IC if it means that a single agent will reach the optimal action in the limit. Similarly here we say a single method is UC if it means that a single agent using that method will reach the optimal action in the limit. Here we say a set or a sequence of methods is GIC if it means some little community where everybody has just one of those methods from that set. If everybody uses one of the methods from this set, and that guarantees that everybody will find the optimal action, then we say that that set of methods itself is GIC. So that set of methods works for some community when they're all employed. And on the other hand, again, we say that some set of methods M is going to be GUC when everybody in sub-sub community employs it, regardless of what's going on outside of them, they're able to find the optimal action because each of them employs that set of methods. Okay, so these are our four contexts these are the four contexts in which a method might work: in isolation, for a particular individual in isolation, an individual in a group of other people using different methods, an individual that's part of a community where they all are choosing from some given set of methods, and the same when that community is part of a larger community that's using various methods. So, right, so the first two, these top two are talking about the idea of a particular method working, and these two are talking about a set of typically, or oftentimes they're similar, or I mean, I suppose you could even think of identical methods existing in this family, but typically they're of the same family. Right? Okay, so these are our four contexts. And so now we can get a little bit better feel. So this table is where I'm going to just basically show all of the results that we're interested in here. Here we have all the entailments that do hold. So what this means is if you have a method that's IC, well then, yes, obviously the method is going to be IC. So this diagonal here is just trivial, right? So any method that's UC is going to be UC. Any method that's GIC is going to be GIC. So all of these on the diagonal is absolutely trivial. So but let's understand the other parts. So for this horizontal here, think of UC, and the fact of UC is that it says, well, if you just give me an individual and he performs some method that's UC, then it doesn't matter what's going on outside of him, he'll still find the optimal action. So more to the point, it doesn't matter if there's people outside of him doing something else. It doesn't matter if there's nobody outside of him doing anything. It doesn't matter if there's people outside of him doing the same thing as he's doing. It doesn't matter what's going on outside of him. Any UC method is going to automatically be everything else. Because if you just have a group of people and everybody is doing a UC method, well, each person doesn't care about what's going on outside, because a UC method says, again, I don't care about what's going on outside of me. I'll still be able to find the optimal action. So a method being UC is actually the strongest condition. It entails everything else. And we'll talk a little bit more about those in time, if we have time. And I don't probably. Okay, so that leaves us with this last case, and that's going to be the same sort of thing. If we have a GUC method, that means some subcommunity is going to be able to find the optimal action regardless of what's going on outside. So regardless of if what's going on outside is absolutely nothing, or excuse me, is absolutely nothing right up here. Okay. So that's those are the entailments that do hold, just based on understanding the structure of our social context. And now to get a little bit of a feel for the particular methods that these agents might actually employ. So I'm not going to try to spend too much time on the gritty details. Instead, I want to just try to give some sense of what's going on in each of these methods to give you an idea of how we get to the findings. But the idea is, right, an epsilon greedy method is going to just, it's always going to want to put all the probability on the optimal action, but it's going to put some epsilon amounts of probability on the non-optimal actions, where that epsilon decreases over time. So over time, we're going to test the non-optimal actions less and less. A weighted reinforcement learning method is going to just, it's going to put probability on moves in proportion to the payoff that we've seen for those moves so far. So one thing that could happen from that is if you see a move A that has that you've seen it's been used 4 times before, and each of those times it's given you payoff of 1. And you've also seen the move B be used just once, but it's given you a payoff of 4. This method is going to make it so that both of these moves are, the chance that you use either one of those moves on the next round, either one of those actions on the next round, is going to be equal, because they've given you the same payoff. So because of that, you might think this isn't the greatest method, because B seems like a greater method. I'd rather choose B than A. I don't want to give as good of weight to A than I would to B, because B seems like it gives a higher payoff. To try to capture that, we have the weighted reinforcement learning, which instead talks about the regret. So you have some upper bound on the utility that you think you would get from your optimal action, and you sum up all of those. So here, if the upper bound was 4, then you would have 0, but here you would have 3, 3, 3, 3. And instead, you would do it in proportion, right, against the things that have a higher regret. Okay, so let's go ahead and continue. Again, for anyone that wants to talk about the nitty-gritty details, I'm happy to do that, but I don't want to spend too much time on those sorts of things. So let's go ahead and continue. Right, so we have simulated annealing next, and simulated annealing is a lot like the delta epsilon strategy, except here we care about specifically what action we're coming from. So if we're coming from a given action, we look at all the other actions we can take, and we put only so much probability on the actions that are worse, that I see as worse than the action I'm doing right now, or that I just did. And so the probability that I take one of those worse actions is going to decrease as time goes on. Early on, I'm okay with trying out an action that's not as good as what I'm trying right now. But as time goes, I'm going to be less and less, I'm going to be more and more stubborn about switching from the action I actually have if the others aren't any better. Delta epsilon also is similar to epsilon greedy, except now instead of just the epsilon that we put on non-optimal strategies, we're also going to put a delta on some set of favorite strategies. So the idea is we're just going to choose exogenously some set of favorite strategies that we're just going to be extra stubborn about. And we're going to just, for no good reason other than they're just exogenously defined as our favorites, we're going to just make sure that we study anything in our favorite set an extra, a good amount before the end. So both of these epsilon and delta are going to decrease as time goes on. It's just that epsilon is attached to some group of favorite strategies, and the delta is just attached to everything that's not optimal. I don't know why I put a Q there. Not optimal at the given point. Okay, so that's simulated annealing. Finally, UCB. This is actually different than anything else we've looked at. Simply put, a UCB doesn't just base its estimate or its value of the various actions based on just the outputs it's gained. Instead, if you haven't tried a particular arm, then what the UCB will do is just leave your confidence interval for what that arm could do as very wide. So you might expect an arm to have a very low payoff, but if you haven't tested it enough, the idea is the interval of your confidence is going to be much higher. And so the UCB method will make sure that you test out anything that hasn't been shown to actually, in fact, have a low expectation. So it's essentially just going to test out each and every method enough until it's pretty sure that until it's pretty sure it's found what the optimal method is. That no method can be shown to be higher than what it's found to be optimal. Okay. Right. So let's go ahead and continue a little bit more. So right, we have a few theorems that help us fill out this box. So so the idea is theorem 3 shows us that we can have IC methods that are not UC, right? And so the easiest way to see this, as well as this will work for another theorem down the line, is if you have some epsilon greedy method. The idea behind an epsilon greedy method is that you need your epsilon function to be finely tuned based on the amount of evidence you're getting. So if you're alone, then the probability that you test one of these non-optimal actions, if it's something like 1 over n, as n continues, right, as n is the number of the round, then we'll be able to actually test all of these non-optimal actions well enough. But if you're situated in some community, then each one of these guys is giving you a lot more evidence about any particular action. So the idea is we're not actually, so if our rate is something faster, we're not actually going to be able to get the chance to test out all the individual opportunities. So again, the idea here is with these epsilon methods, epsilon needs to be finely tuned to the speed at which you get new evidence. Because if you get evidence too quickly, then you're going to dismiss those non-optimal actions too quickly, and one of those might actually turn out to be optimal. Okay, so that's that one. And then we can go ahead and go straight down. So a GIC method that isn't GUC, so we can think of a network that's GIC would be one where we have this subnetwork, and alone, so as the theorem says, alone we can have a GIC network just composed of just RL methods, right? So everyone here is just doing some RL method. But the problem is, if you take this RL method and you situate the same network with the same people playing the same thing, and situate it with a bunch of other people, where you don't know the method that each one of these ones is playing, well, suppose each one of these is just dogmatically playing some obviously non-optimal action. Well, because the RL strategy just accumulates all the payoffs for any action, these could easily just skew the numbers and make it so that all the non-optimal actions just, as a matter of fact, have a much higher cumulative payoff. So if there weren't those other people giving you all that noise, you would have been just fine. But as soon as you situate that community in a bunch of noise, then you don't have, you're not able to find the optimal action. Okay. So that would be theorem 4. Now theorem 5 gives us these next two cells. And so the idea here we can see again with just our the epsilon greedy idea from before, right? So if we have something just alone that the epsilon greedy is nicely finely tuned for, when you put it in a situation where it's either surrounded by, I mean, fine, everybody else is still playing an epsilon greedy, that's still just too much information that'll make you dismiss those seemingly non-optimal things just too fast. And the problem just gets worse if you also throw in people that aren't doing what you want. So the idea is for these IC methods, just take any epsilon greedy strategy with the epsilon function finely tuned for a single learner, and anything more than a single learner is going to be a problem. Okay, so there we have that one. And finally, theorem 6 and its corollary, which we can just kind of think of in tandem. Let's start off with this bottom left cell. So the idea here is we can have a GUC, and so this is going to be probably the most interesting finding. We could have a GUC network, so a network that the subnetwork, everybody's playing some method from M, right? So Mi exists in M. So M1, M2, yada, yada, yada. I won't clutter it with that. But then if we plant that subnetwork, and so for this to be GUC, it not only can find the truth if it's alone, but it can find the truth or the optimal action if it's surrounded by others. So if this subnetwork can find the optimal action, we call it GUC. But what we're saying in theorem 6 is if you just take one of these guys and put him on his own, now he fails. Now he isn't guaranteed to find the optimal action. So to see that, we can just think of one of our delta epsilon strategies. Right, so a delta epsilon strategy forces everybody to choose some favorite action. So what if we had it so that every G in our little subgroup, and let's call this G prime, the network that we're saying is going to that's going to be performing this. What if every G chose their own, just some unique A, such that A is in, right, this, I don't know that this is exactly their notation, but the idea is, what if every one of these individuals chose their own favorite action to pull? And each one of them was essentially in charge of just making sure that action was pulled sufficiently enough. So if you took one, so everybody working together makes sure every action's been done sufficiently enough, and it doesn't matter that other people are giving you extra information because we're making sure to at least explore all of our possibilities. But as soon as you take one of those guys out and put him on his own, now he's just being stubborn and he's just choosing some favorite action and he's not listening to the fact that other people are talking about others. So I think a good example of this is if you took 5 scientists that are each pursuing 5 different plausible theories. If you take any one of those scientists out and you just put him on his own, he's no longer going to be, he's just, in a sense, stubbornly or dogmatically just looking at a single theory, and he's not getting any evidence from people studying other theories. So the idea here is that, so we can kind of transition to, this is the point of the paper, generally speaking, is that we can have some prescriptions that we would want to give to people in a community. Like, so if we had this community of scientists, we would tell them, yeah, it's fine for you to be stubborn and choose one particular theory and only study that one. But that only works if you're in some community where they're doing something, that needs to be carefully described. On the other hand, if you're alone doing something, and we've decided, yeah, no, this as an individual epistemology rule, this is just a great rule, that doesn't necessarily mean that you can take the same rule and give it to everybody in a community and think that everybody in the community is actually going to find the optimal action. So the point here is, the point of this entire paper is to say that there's some methods, there's some prescriptions you would want to give to people when they're in a community that you wouldn't want to give to people when they're just on their own. So the point here is that rationality, to say something is rational, say an update process is rational, depends on what context you put that, that agent in that's employing that. Okay, so one last thing, just a couple discussion questions to look at. I'll leave these here for you to look at, and I'll go ahead and just cut it off now and we can talk about them in the Q&A.